3.1. Outline properties of radioactive isotopes and their half-life that are used to obtain scans from organs. So an isotope is a chemically identically to its parent element, but its nucleus has a different number of neutrons, which means that isotopes have a different mass. So naturally, radioactivity is observed in all isotopes of elements above bismuth in the periodic table. Radioisotopes can also have been synthesized, which has been created in either a nuclear reactor or particle accelerator. And you may have seen that at ANSTO during our experiments conducted there, or even our excursion. More than 400 isotopes are known to exist. Many of radioactive particles that it emits are dependent on its element. So there can be either three particles that is common that you would have learned in years 7 to 10, and those are alpha rays, beta rays, and gamma rays. However, I'm going to also introduce positrons today. So an alpha ray has been found to be a helium nuclei with a double positive charge. Okay, so this consists of 2 neutrons and 2 protons that are bound tightly together and are identical to the helium nucleus. Because of their double charge and large size and mass, alpha particles are absorbed by a few centimeters of air and absorbed by examples such as paper. So such rays are not suitable for medical scanning. However, I've got that in the table in the diagram there. So beta particles are fast-moving electrons, much more penetrating than alpha particles, but still readily absorbed by the body tissue. Beta particles are released when an isotope has a neutron to proton ratio that's far too high for stability. To decrease this ratio, a neutron is transformed into a proton, and then this in the nucleus, and the beta particle is then emitted. So a typical beta equation will be shown in the next slides. Okay. Well, we're looking at gamma radiation, which is the third one on the far right column. So it's an electromagnetic wave that has no charge, and it's got a very, very short wavelength. Okay. Because the gamma rays have no charge or mass, they are penetrating and pass readily through body tissue. Gamma rays are often emitted after other forms of radioactive decay and are most useful types of rays for trace scans. So if you're looking at the table here, we've got the charge and nature of alpha, beta, gamma, ionizing effect, penetrating power, deflection in electrical magnetic field, and their energy. But the fourth one that I'd like to just understand for this video that's not as necessary for the topic just yet, but the word positron, it's a positive electron. So it is emitted from isotopes with a neutron to proton ratio that is far too low for stability. So this is the opposite to what we just learned with the beta particle. So the ratios decrease in such isotopes by a proton decaying into a neutron in the nucleus, a positive electron, so a positron is emitted. All subatomic particles, this is why I'm bringing out positron early, have antiparticles, and the positron is an antiparticle to the electron. These particles are used in PET scans, and we will discuss this in the 3 dot whatevers. Okay, so looking at the 3 that are in the video, types of radiation, alpha, beta, gamma, but you've also got positron emissions or particles. What is a half-life? So the time for the half of the isotopes in a radioactive sample to undergo radioactive decay is called the half-life of the isotope. Okay, so the half-life is unique to each element and may vary from microseconds to millions of years, and you'll learn how critical that is when you're looking at radioactive isotopes for medical diagnosis. Okay, so a very big slide with a lot of content that I've just discussed. However, if you just copy the table down neatly in your books, it's a great start, and also looking at the definition of an isotope, a radioisotope, and what a half-life is.